Hello, welcome back. In this video we'll discuss the helium neon laser. The helium neon laser is the first gas laser to be operated successfully in 1961. As any other gas lasers, this laser also works on the principle of stimulated emission of radiation. Now we shall see the construction of helium neon laser. In the case of a helium neon laser, we take a mixture of gases, namely helium and neon. A mixture of helium and neon are taken in a quartz tube. These two gases are taken in 10:1 ratio. Helium and neon are taken in 10:1 ratio in a discharge tube. Here the discharge tube is made of quartz. The dimensions of the tube are about 80 centimeters in length and about 1.5 centimeters in diameter. The dimensions of the discharge tube are about 80 centimeters in length and 1.5 centimeters in diameter. So the length of the discharge tube will be about 80 centimeters. The diameter of the discharge tube will be about 1.5 centimeters. Look at this diagram. In this, we have the discharge tube. The entire quartz tube is the discharge tube. We have an anode here and we have a cathode there. And this discharge tube is filled with helium and neon gas mixture. We have two slant glass windows, let us say W1 and W2. Similarly, we also have two mirrors. One mirror is here, we call it as M1. And this mirror we call it as M2. We have a discharge tube made up of quartz crystal. In that we have the helium neon gas mixture. The tube has two slant windows, W1 and W2, and the entire tube is enclosed by two concave mirrors, M1 and M2. Placed parallelly, two glass windows are arranged at Brewster's angle to produce plane polarized light. What is Brewster's angle? Brewster's angle is the angle of incidence for which the reflected beam will have the highest component of plane polarized light. Generally, the Brewster's angle theta is given by tan inverse n, where n is the refractive index. We have two concave mirrors M1 and M2 that are made up of some dielectric, could be a glass, on both sides of the quartz tube. These two concave mirrors are arranged in such a fashion that their foci lies within the interior of the discharge tube. Two concave mirrors M1 and M2 are arranged on both sides of the discharge tube so that their foci lies within the discharge tube. Here, mirror M1 is a 100% reflecting mirror and M2 is a partially reflecting mirror. Laser emerges from the M2 mirror. These two mirrors M1 and M2, they do the job of the optical resonator. These two mirrors, they enable sustained oscillations of the radiation within the discharge tube. Mirror M1 is 100% reflecting mirror, which means all the light that falls on this mirror will be reflected back, while mirror M2 is a partially reflecting mirror. Since M2 is partially reflecting mirror, the laser will come out of the discharge tube or the optical arrangement from M2. Now we shall look at the working. In the case of a helium neon laser, the helium is maintained at a pressure of 1 mm of Hg, while neon is maintained at 0.1 mm of Hg. In the case of helium neon laser, neon atoms are the active centers, which means lasing will come out of only the neon atoms but not from the helium atoms. When the electric discharge takes place in the discharge tube, electrons would move between the electrodes, and these moving electrons, they pass through an electric field, thereby their kinetic energy is improved. When a collision between the electrons and the helium and neon happens, kinetic energy of the electrons is transferred to the helium atoms. Electrons produced in the electric discharge are accelerated to increase their kinetic energy. Collisions of these accelerated electrons with helium atoms in ground state will transfer energy. As a result, helium atoms are excited. Let us say that E star represents The electron possessing high kinetic energy, when it collides with a helium atom that is in the ground state, gives rise to a helium in its excited state and an electron that has lost its kinetic energy. So collisions between the fastly moving electrons and the helium atoms will take place in the discharge tube. As a consequence, electrons will transfer their kinetic energy to the helium atoms. Thereby, the helium atoms would go to the excited states, and electrons, they will lose their kinetic energy and keep moving in the discharge tube. Helium atoms are excited to F2 and F3. We are representing the energy levels corresponding to helium with F and the energy levels corresponding to neon with E. So when the electron interacts with the helium atom in its ground state, the electrons will transfer their energy to the helium atom. Excitation of the helium takes place. The excitations will be from F1 to F2 or F1 to F3. So it essentially depends on the kinetic energy of the electron. If the energy is more, then the transition would occur from ground state to F3, that is F1 to F3, and if the energy is slightly less, then a transition from F1 to F2 takes place. And in this case, why helium is chosen in the case of a helium neon laser is because of these two energy levels, E6 and E4. These two energy levels are close to F3 and F2. Energy level F3 of helium is at the same level as that of the E6 of neon. Similarly, energy level F2 of helium is almost at the same level as that of the neon E4 energy level. Because these two energy levels are close to these two energy levels, we have used helium in the case of a helium neon laser to transfer the energy to the neon atoms. Ultimately, we'll be transferring energy to the neon atom so that the neon would go to either E6 or E4. We use the helium as a mediator to transfer the energy to the neon atoms. The collision between the excited helium atoms and neon atoms will result in the excitation of the neon atoms. The excited helium atom make collision with the ground state neon atoms and force neon atoms to excitation to E6 and E4. In the neon atoms, E4 and E6 are metastable states. Here, excitation is happening when collisions between the excited helium happens with the neon atoms, gives rise to neon in its excited state and the helium in its ground state. In this case, the transfer of energy is called as resonant energy transfer. Why it is called resonant energy transfer? Because the energy levels F2 and F3 are almost equal to E4 and E6. F3 is almost at the same level as that of E6 and F2 is almost at the same level as that of the E4. So whenever the helium in its excited state interacts with a neon atom, it transfers its energy due to the resonance, and as a result we have the neon in its excited state and helium in the ground state. So this is how energy is pumped into the neon atoms or the active medium. Since E4 and E6 are populated now directly, population inversion is achieved between E6 and E5, E6 and E3, and E4 and E3. We shall revisit the energy level diagram now. We are pumping neon atoms to E4 and E6 energy levels. A population inversion occurs between E6 and E5. Similarly, a population inversion also occurs between E4 and E3. Another population inversion also occurs between E6 and E3. E6 and E4 are metastable state. A downward stimulated transition from E6 to E5 will give us 3.39 micrometers of radiation. Similarly, a downward transition from E6 to E3, this will give us 632.8 nanometers or 6328 angstroms radiation. And a downward transition from E4 to E3 can give us 1.15 micrometer radiation. So, from a helium neon laser, one can obtain three different wavelengths. However, the optical resonator should be designed in such a way that it can allow operation of only one particular wavelength. Largely, helium-neon lasers are used in this wavelength, that is 632.8 nanometers. Transition from E6 to E3, which gives rise to 632.8 nanometers. That is the general operational wavelength of the helium-neon laser. But it can be made to operate in the other two wavelengths also. The transition can produce 339 nanometers, 632.8 nanometers, and 1.15 micrometers. After the emission, the neon atoms, they make a downward transition from E3 to E2. This is a spontaneous downward transition. A downward transition from E3 to E2 is a spontaneous downward emission transition, and the emitted radiation will be dissipated in all possible directions. After which, neon atoms will make a downward transition from E2 energy level to the ground state, that is E1, while making collisions with the quartz tube. This is a non-radiative process. Using a helium-neon laser, one can obtain optical powers from 5 milliwatts to 50 milliwatts. Essentially, a helium-neon laser is a low-power laser. In this video, we have started by stating that helium-neon laser is the first gas laser to have been successfully operated in 1961. We have seen the construction of the helium-neon laser. We have said a mixture of helium and neon gases are taken in a quartz tube in 10:1 ratio. The dimensions of the tube are 80 centimeters in length and close to 1.5 centimeters in diameter. We have seen that there are two slant glass plates arranged at the Brewster's angle. We have seen what Brewster's angle is, and we also said that there are two concave mirrors on both sides of the discharge tube. One of them is having 100% reflectance, while the other one is a partially reflecting concave mirror. The laser comes out of the arrangement from the partially reflecting mirror. We have said that helium atoms, they are maintained at 1 millimeter of Hg, and neon atoms are maintained at 0.1 millimeters of Hg. Neon atoms are the active centers in the helium-neon laser. We have seen how energy is transferred from electrons to the helium and from helium to the neon atoms. We have seen how the resonant energy transfer mechanism takes place in the case of a helium-neon laser. We have seen the various energy levels and the population inversions that can be achieved in neon atoms, and we have also seen the possible wavelengths that can be emitted from the helium-neon laser. However, we have said 632.8 nanometers is the radiation in which generally the helium-neon lasers are operated. From the helium-neon lasers, one can obtain optical powers of 5 milliwatts to 50 milliwatts. The power of the helium-neon laser essentially depends on the potential difference that we apply across the electrodes of the discharge tube. Thank you.